So today we're going to be talking primarily on the UV disinfection front and why we're going to be using UV versus other forms of treatment. It doesn't mean that we can't go with any chemical oxidation or any kind of residual for disinfection, but we're going to be focusing on the UV front today. Good morning, Joe. Thank you for joining. Okay, so this is a part 6 of a 12 chapter series that we're going to be going through. We've kind of divided them into different parts so we can kind of get them all done, and I promise we keep it under 20 minutes to make sure that we can cover as much as we can. So for those of you that are new with us or that are just logging in, the AWC, we design and manufacture water and wastewater treatment plants. We have been around for over 40 years. We have close to 600 plants operational worldwide, with a lot of new ones coming up and some fun ones in store. So it's kind of what we do. We manufacture everything in-house, so we have a good fabrication shop in Langley, BC. This is about half hour east of Vancouver, on the west coast of Canada. Sorry guys, we're still admitting more people. Give me a second. Here we go. So we primarily divide everything into 3 sectors. So we're going to have our wastewater side for MBR and MBBRs. Then we have our modular potable systems, which is going to be everything that's to do with clarifiers, dissolved air flotation, and of course we have our skid-mounted systems as well, which includes UV pressure filters, ultrafiltration, reverse osmosis, and desalination. Today we're primarily going to be touching on UV. Something that makes UV very versatile is that we can use ultraviolet disinfection, and you can tie it into every single one of these. Whether you're going from desalination to wastewater to treating for arsenic, you will always have a disinfection element of it, even when we're going with wastewater and for wastewater discharge. So what is UV and how does it work? So ultraviolet light is basic. It's something that's not only part of the light structure, but it's something that is invisible to the naked eye. Now, there's something that's labeled as a germicidal wavelength, and which is anywhere between 200 to 300 nanometers. The one that we primarily choose that we're going to be using for ultraviolet, the magic number is 254 nanometers. So 294 nanometers is the most germicidal spectrum that we're going to be using whenever we do UV disinfection. Now, why is it preferred in the field? Is because there is no chemicals involved. We're not adding anything to the water. The key thing is that we're not adding anything to the water. We're not eliminating anything from the water. Where all we're doing is we're inactivating contaminants, in this case, pathogens. You'll notice that we're going to be using the word inactivate, and we're not going to kill, and we'll get into that here in the next minute. So what are we doing? When we have the microorganisms are exposed to the water, we've got lamps that are going to be sitting inside of a chamber. As water flows through the lamps, that's how we're inactivating it. The basic thing is we're scrambling the DNA for your bacteria. This applies for bacteria, viruses, and protozoas. So we normally measure UV in millijoules per centimeter square or microwatts per centimeter square. So we're going to be jumping between the two of these. Easy conversion here is it's 10,000 equals 1. So 1 millijoule per centimeter square will equal 10,000 microwatts per centimeter square. Some of the charts that I have up ahead are kind of a big mix between the two. We're going to try to stick to one versus the other. I like using millijoules because it's a lot smaller, but you'll see that we kind of interconnect between the two of them. But it's an easy conversion, 1 to 10,000. So we're going to focus on the pathogens. So when we are using UV, again, we're not looking at removing anything. We're not adding anything to the water. We're using it for disinfection and disinfection only. And what we're doing is we're going after microorganisms. Microorganisms fall under the pathogen family, and there are 3 particular pathogens that we're going after, which includes bacteria, viruses, and protozoa. Now, of course, we're going to break those down into a little bit more. When it comes to bacteria, we're going to go after E. coli and coliform. These are very common, and this is primarily waterborne pathogens that you're going to see in the water. On the viruses front, you'll see that we have hepatitis A, adenovirus, rotavirus, legionella, and cholera. Adenovirus is either adenovirus or adenovirus. You're going to see it both out there. Of course, we can't talk about viruses without mentioning coronavirus. While UV disinfection will work for coronavirus, or COVID-19, interesting enough, is the coronavirus does not last very long in water. So whether you're hitting it with UV or not, for the most part, by the time you hit it with UV, it probably wouldn't have lasted that long in water. So it's not considered a waterborne illness, other than on the wastewater front. That might be a different consideration. And then when we go into protozoas are basically cysts, any kind of cysts. The two ones that you primarily see in surface water are Cryptosporidium and Giardia. Those of you that are familiar with, the outdoors, you're going to hear a lot of crypto. If you ever see beaver fever or the itch, sometimes they call it the itch. It's pretty nasty stuff. Those are all cysts that are going to be found in surface waters, primarily when waters are warmer. And the same thing applies to Giardia. These are all cysts. And they're larger in size. You can potentially mechanically remove them, but we're focusing primarily on making sure that we inactivate them with UV disinfection. So why are we using UV? We use UV because it's not only highly effective at inactivating microorganisms, but it actually does a better job than chlorine. When we use chlorine disinfection, the chlorine needs to have what's known as CT time or contact time in order to permeate through the bacteria or the cysts, and because of that, it's got a very strong outer shell. When we're using UV, you can actually go right through the shell and penetrate the shell without needing that contact time that you would require for chlorine disinfection. Another big advantage, of course, is that it doesn't change the aspect or the physical attributes of water. So the water is going to taste good. If it was coming in good, it's going to come out tasting good. Again, if the water wasn't tasting good ahead of time, it's not going to taste any better after. Okay, so UV does not add or remove anything from the water. One of the better portions of using UV disinfection, of course, is that it does not form any trihalmethanes or disinfection byproducts. Unlike with chlorine, whenever you add chlorine to water that has any organics in the water, you can potentially form disinfection byproducts, which then are a lot harder to remove. And now when you're trying to eliminate chlorine, you're also having to try to remove both the chlorine and any disinfection byproducts or trihalmethanes or HAAs. And of course, there's no chemical handling requirements. So that means that operators aren't having to go out into the field and they're not having to fiddle around or transport any chemicals. Now, that being said, it doesn't mean that UV will always be your only form of treatment. You will potentially be using UV disinfection along with something else. But when you use disinfection, we normally have two forms of treatment, or what's known as two barriers. So the two most common barriers would be UV disinfection, and of course you would have your chlorine or any other oxidant that you use for disinfection for residual. So important parts to consideration when we're using ultraviolet. Pre-treatment. I can't say this enough, the pre-treatment to using UV is very important. Of course, like I mentioned, it's not as effective as chlorine because there are specific viruses that can't be inactivated with UV alone, or they need very high doses of UV in order to be inactivated. We're going to touch on dosing here in a minute. And then, of course, the biggest drawback is there's no residual downstream. So for those of you that might not be directly related in the water industry, residual basically means the amount of free chlorine that's in the water that will actually continue being disinfected. UV is a barrier, and it should only be considered a barrier, which basically means is you're putting up a wall, you're disinfecting any water that's going into your chamber or into your wall. Anything after that is not going to be completely treated. So if you're going into a city where you have 200 miles of pipes, that doesn't mean that all 200 miles of pipes are going to be disinfected. It's just all the way coming out of the treatment plant. So dosage, I kind of touched dosage a little bit earlier, but we're going to go into it a little more so that you have a better understanding of what dose means. So different microorganisms or different pathogens are disinfected or inactivated by a different dose. It's the same thing why you wouldn't use the same mouse trap for a mouse as you would use for a grizzly bear, okay? So they all have different specific doses for log reduction. So we use log reduction, and you'll normally see it as a 4-log or a 3-log or a 6-log, which is used in California. What a log reduction basically means is, an easy point to remember is how many decimals there are. So a 4-log reduction basically means that you will remove E. coli at 99.99%. But it's all measured in dose, and what dose we're going to be hitting it, which we're going to go through it here in the next bit with a nice little chart. So easy way to take a look at dose is UV dose is a function of intensity and time, okay? So how much light we're hitting it with and how much time it's exposed to the light. So that's what gives us the UV dose. So before we go into it, we're going to cover UVT, which we're going to be going over a lot. So UVT basically stands for ultraviolet transmittance. So here's a kind of clear example of what works through water in ultraviolet transmittance. Ultraviolet transmittance is basically how much UV light is going through a column of water. So UVT meters, what they would typically do is they'll have a centimeter of water, they'll put it in a water column, they'll shine some UV light at 254 nanometers through the light, and then pick it up on the other end. If your water is really dirty, it's considered 0% UVT. If you've got okay water, it's at 40%. Really good water is at 100%. You would rarely see water in nature at 100% UVT. You're normally looking at a range of anywhere between 75 to 85. We want to make sure we have a minimum 75% UVT transmittance with any kind of UV disinfection. So here comes the fun part. Dose. So like I mentioned, dose is a clear reflection of UV light intensity and time, and it kind of converts into what our flow rate is. So if we have a very high dose, but we're running at a very high rate, that means that our intensity starts dropping because of the now quote unquote contact time, right? So it's very important to match our dose and our flow rate in order to get our UV intensity time. Ultraviolet UVT is also very important. So the lower the UVT you have, the lower the dose. The higher the UVT, the higher the dose. And here's a kind of a clear reflection of what we have. So on this end, this is microwatts per centimeter square. I guess we could have converted to millijoules per centimeter square. But the US EPA sends a very specific standard of a minimum. So any kind of UV system needs to hit a minimum of 40,000 microwatts per centimeter square. So let's just think of that as 40. So 40 millijoules per centimeter square. So you have a quick correlation of how you would work this. If you have a chamber that can handle 100 gallons a minute, and it's operating at 40,000 microwatts at 70% UVT. So if we were to get the same one and bring our water up to 90% UVT, so now we have cleaner water, now we're hitting a dose of 70,000 microwatts per centimeter square. So it's quite a bit higher. And the same thing applies if we go this way. If we restrict our water, instead of having a chamber that can handle 100 gallons a minute, we put in a restriction. And oh, we have somebody else joining us. Give it a second. If we have a restriction and we bring it to 50 gallons per minute, by hitting it at 50 gallons a minute, we're actually increasing our dose to 80,000 microwatts per centimeter square. So that kind of gives you a correlation of how the ultraviolet transmittance on this end and our flow rate equals our dose. So this is the dose that we're trying to achieve. Again, anything over 40 is good. So basically anything on this end and anything on this end. And the same thing applies. If we were to get one of these, if we were to get this same chamber, so same UV system that's rated at 100 gallons a minute, we were to bring it down to 100% UVT, so really clean water, good pretreatment, and we choked it down at 50% capacity, we're now achieving 220,000 microwatts per centimeter square. Okay, like I mentioned that not all mouse traps are created equal. We won't use the same thing if we're taking out a mouse or we're taking out a grizzly bear. This is the inactivation of viruses. As you can see, every single one is reflected at a very different dose. So here's what we have, the 3 log reduction versus a 4 log reduction. And we have Crypto and Giardia, as you can see, are achieved at inactivation at a pretty low dose. So we're doing 6.4 millijoules per centimeter square or 7.9. So it depends, 3 log versus 4 log. And you'll see all of these, 6 log, 10 log, 4 log. We saw here, the US EPA, the NSF, which is the National Sanitation Foundation certified standards, are all set for a minimum of 40 millijoules per centimeter square. As you can see here, the inactivation of every single one of these viruses is well below 40 millijoules per centimeter square. So the same thing applies to the polio, rotavirus, Legionella, Salmonella, the list goes on and on. There is a slight exception, and that is to the adenovirus or the adenovirus, which is the inactivation for 4 log reduction is 186 millijoules per centimeter square. So it's very, very high. So if you ever have to go after an adenovirus, be rare that you would have to go behind adenovirus, but if you ever had to go specifically after adenovirus and that was what's being targeted, again, you basically get a system, you make sure that you, to use a lack of a better term, choke it down, you flow restrict it, within a range where it can achieve closer to 186 millijoules per centimeter square for 4-log inactivation. So the feed water quality. Just as we were discussing the ultraviolet transmittance and the importance of UVT, the feed water quality is very important, and the pretreatment pretreatment is just as important as your UV dose. So things that will interfere with the water, of course, are turbidity. So picture that you've got any kind of turbidity, or which is a fancy word for dirt. If you have any kind of dirt in the water, your bacteria or microorganisms are going to attach onto the turbidity. When you try to hit it with UV light in order to disinfect it, there's going to be shadows in the water, which basically means it's going to not achieve the level of inactivation that you're trying to achieve. So that's why turbidity, you will always have UV manufacturers will always have a minimum of a 5-micron pre-filter going through any one of their systems. Okay, that affects turbidity. Hardness. Hardness is important. So hardness is, of course, it's a dissolved. We're going to find calcium carbonate in our water. So it's not necessarily that it's going to be interfering with the treatment per se, but it's going to be interfering with the maintenance. So hardness is going to start building a scale of line formation of calcite formations over your sleeve. And when you build over your sleeve, or you're interrupting the UV disinfection portion of it going into the water, that's why it needs to have some kind of pretreatment. There are some nice sleeve wipers that are in the larger systems. So if you're going in the 400 or 500 gallons per minute, there's sleeve wipers that will constantly be moving back and forth to keep your sleeves as clean as possible. If you don't have those sleeve wipers, then you need to keep it under 7 GPG or 120 milligrams per liter of hardness. Same thing applies for iron and manganese. Of course, you know, iron and manganese, as we've touched before, will stain anything and everything. You start putting hot water into it, and it's going to get even worse. So what you're doing is you want to make sure that you pre-treat for any ferric oxides or any manganese so that we don't have the sleeve contamination. Which brings us over to organics. Now, organics are not potentially going to be fouling up your UV sleeve, but what they will do, however, is organics absorb UV light. Okay, organics and tannins is much like discolored tea. It's what you would have if you look into a lake and it has that greenish, bluish tone to it. It just basically means it's got some level of organics. So what we do is we need to make sure that we pre-treat it, and you're testing for organics. That's very important. If there are certain levels of organics below 1 milligram per liter, however, if your UVT, your ultraviolet transmittance, is over 75 to 85%, then you can potentially use UV disinfection. You just want to be aware that if your organics are higher than that, you should be testing for UVT, and it will be a clear reflection of how much organics are in the water. And the same thing is the other way around. If you are not testing for organics and you test for UVT, and you see that your UVT is lower than 75%, then you should definitely test for organics and tannins. So here are the standard components. How are we doing for time? Oh, right on time. Okay, so here are the standard components that you would see inside a UV system. Again, this is a slightly smaller one, and we'll take a look at the bigger ones in a bit. So this is known as a reaction chamber. So our UV light is going to be sitting inside of a reaction chamber. We've got a controller. Well, it's not reflected in the picture. It's just a power bar. We've got our UV sleeve, a quartz sleeve. So this is a quartz sleeve that sits inside of the chamber. Then we're going to put a lamp. We have a lamp inside of the chamber, which is, these are different kind of lamps that we have. There's a lot of different kind of lamps that are around for technologies, amalgam, high output, low output, pressure, etc. This is just basic components. We have our UV intensity sensor. So this is a sensor that's going to measure the intensity coming off of the lamp through the small water column. And then, of course, we've got our flow meter. So these are some of the basic components that you would see in whether it's a residential, commercial, or even municipal. Even when you go into large municipal systems that are operating at 2,000 or 3,000 gallons per minute, you're still going to be seeing the same basic components. So this is what you would use when you're going into something more on the light commercial side. So you can range anywhere between 10 gallons a minute to potentially 50, 80 gallons a minute. Once we go into something a little bigger, on the municipal front or industrial front, we go into something like this. Again, we still have our chamber. We still have our lamps and sleeves on the inside. As you can see here, this is a UV intensity monitor. This one is not going to be using 8 lamps. This is actually going to be using closer to 12 lamps. I apologize for the brand, guys. I should have blurted that out. That's just one of the ones that I found. Here's another one. So talk about lamps. So instead of going to 1 lamp or 12 lamps, here, as you can see, is there are multiple bank systems. So in this one, I believe they're using 36 lamps. You could potentially add another bank with an additional 12 lamps right here, much like this, which would include your flow. Like I mentioned, UV intensity gives us our dose, which dictates our flow, and vice versa. So it's kind of a little triangle. So if we want to increase our flow, we could potentially add another bank. And if we're operating at anywhere between 800 to 900 gallons a minute, and we need to go up to 1,500 gallons a minute, we would have a different bank. So this is when it goes into the municipal market. And then once we go into the wastewater, it looks like this. Slightly different function. You'll notice that we do no longer have a chamber. This is actually more of a, well, I call it a trench. I know that there's a better word for it, but this is just a side stream of it. So these lamps are also sitting in the water. Again, we're using for UV disinfection any water that's coming off of a wastewater treatment plant, including ours. These actually lift. As these lift, you can do maintenance to it and have access to the lamps. The lamps still fit inside of a UV disinfectant, inside a quartz sleeve. So each one of these little knobs here is a lamp, and inside of the power controller will tell you how many lamps are on, how many lamps are off, and they'll have a small little sensor on here to tell you which ones are in operation. So this bracket right here lifts off, and you can actually take a look at what the status is of the lamps. Common problems. Common problems with UV, and I insist, pre-treatment, pre-treatment, pre-treatment. You have no idea how many of these systems that have issues, where they're primarily, the only issues that we're having is because there are some lamp fouling or water quality. So we discussed the things that are going to be interfering with our UV disinfection are going to be water hardness, iron, organics, turbidity, and which will all cause low UVT. So if you have low UVT is caused by everything that you have up there. So that's why the pre-treatment is so important. So I believe that is it. So I promised we were going to keep it at 20 minutes. We're at 23 minutes now. So we try to keep it as short and sweet. If anybody has any questions, you can go ahead and type it into the chat so I can try to answer some of them. For those of you that are logging in here for the first time, make sure you follow us on LinkedIn. We're pretty active there. We're trying to post some of the new things that we're working on. I'll give it there for another minute if you guys have any questions. For next week, John Stanis is going to be joining us Thursday, 10 o'clock East Standard Time, and we're going to be going over, let me see here. I don't know if I have a quick preview. No, possibly not. So John Stanis is going to be joining us, and we're going to be doing a specific 20-minute deep dive into dissolved air flotation, how the chemistry goes around it, some of the, not just the chemicals and polymers that we're doing, but we're also talking about the skimmers and the belts and how they move and some of the basic aspects of how we cover dissolved air flotation. So if we don't have any questions today, thank you very much, everyone, for your time, and I'll see you next week. Bye.